Okay, students, now comes another question number 22, and now here you are given a function and you are going to analyze whether this function is continuous at 2 or not. So as usual, I strongly recommend you to subscribe and share the channel and to give comments, like for this particular channel. Now let's directly go to the question. It says check whether this function at x equals 2 is continuous or not. So what we need to do is we have to first remember how a continuous function is defined at a certain number. A function is said to be continuous at a number if three conditions are satisfied. So in our case, our number is number 2. So we have to check the following three conditions. First, check whether 2 belongs to the domain of f or not. Clearly 2 is part of the domain because as can be shown here, the function is defined at 2 because it says x less than or equal to 2, so 2 is included here. This shows you that 2 is part of the domain of f. Even you can know what f of 2 is, because f of 2 is nothing but it is 2 squared plus 1, you see, because at 2 it's defined, it's 5. So this shows you that 2 is part of the domain of f, so the first is assured. Second, check whether the limit exists or not at 2. You have to check that one. For this case, we need to get closer to number 2 from the left and from the right and check whether equality is attained or not for this particular limits of function. Number 3, not only the existence of the limit that needs to be assured, we need to also check that the limit must be the same as f of 2, okay? It must be the same as f of 2. So once we assure these three conditions, we can say that the function is continuous at 2. But if we face one failurity in these three, at least one failurity in these three, the function is not continuous. It's not continuous means the function f doesn't have a continuous plot, okay? Instead it will have a certain gap or a certain hole or something like that, okay? It will never be continuous. So let's assure now this. So let's check the second one because the first is already done. When we come to the second one, you see we have to check whether the limit of the function exists at 2 or not. So for that, limit of f of x as x approaches to 2 from the right is considered. So here, as you are approaching to number 2 from the right side, you are considering numbers greater than 2, and your function for numbers greater than 2 is the lower one, students, because whenever x is greater than 2, you see, you need to take the function 3x minus 2, it's written. That's why I'm taking this f of x to be 3x minus 2 here. So we can directly put number 2 in place of x, and 3 times 2 makes 6, 6 minus 2 is 4. So the function gets closer to 4 as we are approaching to 2 from the right side. Now let's directly go to approaching to the function as we are approaching to number 2 from the left. So the function approach to number 5, as you see, the reason is because the limit as x approaching to 2 from the left is written, but now as you are approaching to number 2 from the left, you are considering values like 1.9, 1.99, something like that, because these numbers are, you see, close to number 2 and less than 2 as well. So we have to use the upper expression x squared plus 1 because we are considering numbers less than 2. So this is going to come. Now, in order to find the limit, nothing hinders us not to substitute, so we can directly put number 2 in place of x, and then 2 squared plus 1 makes 5. So dear students, we have obtained now two different limits. See, approaching to 2 from the right has made 4, and approaching to 2 from the left has made 5, but these two are quite different. Therefore, the limit doesn't exist, students. The limit doesn't exist, so property number 2 has failed. Okay, because of this, the function is not continuous at number 2. Okay, the limit doesn't exist at 2, hence the function is not, see, continuous at 2 because the second criteria has failed. The limit needs to exist at a particular number. Okay, and you proceed to the third provided that the second is assured. Okay, so I hope you've understood. Now let's directly go to the next question number 23. And here it says discuss whether this function is continuous at x equals 0 or not. So as you see, the function has been split into three different expressions at 0. For whatever x value you may take, if that is positive, the function is cos x, students. And again, for whatever x value you may take, if that value of x is negative, your f of x is the parabola opening downward, which actually is 1 minus x squared. If x is 0, the function is 0. So now, even the function is defined at 0 here, because when x is 0, look, the function is 0. That is to say, f at 0 is 0. F at 0 is 0. So clearly, the function is defined at 0. So the first condition is assured. Anyway, now let's proceed to each of these three cases. So here I go for the first one. For a function f to be continuous at 0, as I said earlier, we have to assure those three conditions. Number one is whether the number given is part of the domain of f. So yeah, it is clear that 0 is an element of the domain of f, because at 0 it's already defined. Next, we have to assure number two, the limit should exist at 0, students. That is to say, the limit of the function as we are approaching to 0 from the left should be the same as the limit of the function as we are approaching to 0 from the right. So now we need to assure each of these two. So later I will show you that. And next, this needs to be assured. The limit not only should exist, but also it has to be the same ways f at 0, students. So now let's pass through to the last two sayings. So look, the limit of the function as x approaching to 0 from the right. So which expression do you think shall we take here? Look, as we are approaching to 0 from the right, we need to consider values greater than 0. So the upper expression must be taken cos x, right? So we directly take cos x here. So can we directly put 0 in place of x? Is everything comes meaningful? Yeah, we can put 0 there. Cosine 0 is 1. So approaching to the function, approaching to 0 from the right, the function gets closer to 1. Yeah. Now let's see what's going to happen as we are approaching to 0 from the left for this particular function. So as you see, the limit of the function as x approaches 0 from the left. Look, in the case of this, now we are considering negative numbers because we are approaching to 0 from the left side. So we need to consider values which actually are negative. So in the case of this, our function is going to be the bottom one. You see, students, 1 minus x squared. This 1 minus x squared is going to be taken. So directly you put that 1 minus x squared. So again here, since this is a polynomial, we can directly put 0 here, and then 1 can come. You see, guys? Here, unlike the previous one, in the case of this, we obtained the limit of the function approaching to 0 from either side to be what? The same. To be the same, here it says not equivalent to 2, but please correct that. It is equivalent to 2, students. So this is obtained to be the same. Hence, we can say that the limit does exist at 0, student. It exists at 0, as you see. So if it exists at 0, there is one thing remaining here, and that is we have to assure the third condition. And that is the limit of f of x as x approaches 0 needs to be f of 0, okay? So that is already calculated, as you see. The limit of the function, okay? The limit of the function. So students, I have now the function being continuous at x equals 0, but I just have modified something here. You see, I won't tell you that. And that is, you see, at 0, I have said here 1. Previously, you were having 0. But for the sake of, you see, showing continuity, I just have made this to be 1 because I have done one example for the case of discontinuity, and I want to show here the case of continuity. That's why I intentionally make this to be number 1. Look, previously this was 0. Now I just have modified that to be 1. So students, now the limit exists because all the three are satisfied. These three properties are satisfied. 0 is an element of the domain of f, yes. And how do you know that? Because at 0 it's defined, f at 0 is 1. Look, f at 0 is 1, it's already done here. The limit should exist at 0, yes. We have assured that limit of the function as we are approaching to 0 from the right, and from the left we do have 1, as you see. And the third, the limit of the function as we are approaching to 0 must be the same as f at 0. So the limit of the function as we are approaching to 0 is obtained to be what? 1, because here we obtain 1, 1. And as I said earlier, make this to be equal. This is wrongly written. It's a matter of copy and pasting error. And then f of 0 is, f at 0 is 1, as I said earlier, f at 0 is 1, so the limit exists and the third property is also satisfied. And because of this, the function is continuous at 0. I hope you have understood.